Having to wait for 9 minutes for the talk to start is certainly a bit frustrating. Um, but truth be told, that's about as much time as I spend waiting for my build each day. So, it's not new for me. And I'm pretty sure that it's not new for you either. And in fact, it's probably a pain point for all of us who write in software in Rust. And so today I'd like to tell you a bit about it. And well, I'm Piotr, and I work for that industry. We we're just working on the next IDE that's written in Rust, and I'm mostly working with language servers and also a debugger recently. Um, what else? Well, I just like compilers in general, even though I haven't written one myself. And then I have a C++ background. I started with C++ like 7 years ago, so that made it quite easy to transition into Rust because the build system or the builds are quite similar in both of these languages. But then I'm not anyhow involved with Rust project, as in I'm not the member or anything. I just look at the build profiles and try to make sense of them. So take what I say with a grain of salt or even the whole salt pincher, if you will. So compile times. Well, who cares? For one, as I said, I do. I spend about 7 seconds waiting for my build each time I make even the simplest change, which that's not a lot, but it does add up. And then I have quite a beefy machine, so I suppose it might be even worse if I were to run on a lower end hardware. But then if you also look at the results of the Rust survey throughout the years, it's a frustration for all of us, I feel like. And when we talk about Rust, the compile times usually come up. In fact, they came up even on today's keynote that I attended. So it just goes to show, and we've just lost the visuals, which is great. Okay, cool. So the problem with compile times is that you cannot really optimize upfront for them. So we don't mind the compile times when you have like a greenfield project because they're like all nice and shiny. You're just not waiting for the builds at all. At some point, they might become a problem, but you probably don't want to spend all the time that you could use to develop features on the compile times, and that's honestly pretty fair. We're engineers, we're not supposed to just look at the build profiles all the time. But you might at some point find yourself waiting for builds more than you actually spend time like coding. So that's probably the point at which you should look into your build. And the issue is kind of exacerbated by the fact that there is no single reason for slow build. I mean, some people will say that Rust is slow to compile due to the borrow checker. Somebody else will tell you that it's the code gen and you should use crane lift. But the truth is, there are some reasons or like some food guns that might apply to community at large. You really should profile your build because it's unique, and there sadly is no silver bullet there to make them fast and shiny. And so in this talk, I won't offer any cures, any silver bullets, because at the end of the day, you have to profile the build yourself. I'll just offer some ways to find the answer. So let's start with cargo, because there are really two components to the Rust build. There is rustc, which compiles a single crate, and then there is cargo, which does the dependency management. It also does build scheduling. And then finally, that's a thing that's purely about cargo, and rustc is not involved in it that much, the build script. And actually, I want to talk about build script first. Even though this talk is about optimizing compile times, you might find yourself, especially in incremental scenarios, running into the spurious rebuild of your workplace. And as I said, that's purely a cargo problem, which you can diagnose with cargo build verbose. So on the slide here, I have like a rundown, and at the top here, you can see each of these lines has a reason for the rebuild of a given crate. So cargo just goes through all of your crates and determines whether it has to rebuild it. And at the top here, you can see that the editor crate is dirty because one of the source files has changed since the last build. And this is cascading in that the cargo will rebuild all of the dependents of the crate that gets rebuilt. So if one of your dependencies happen to be previously rebuilt, that will just significantly lengthen your iteration time. And once again, this isn't purely about optimizing the compile time here, but it's an issue that you might run into when, for example, your IDE crushes the cache that cargo has for itself, for its build. And so, yeah, it's not. Hopefully, it's not a problem for you, but it's still worth knowing about because this really is the only tool to diagnose these kinds of issues. But as for actually improving your compile times, the one thing that I reach for the most with cargo in particular is the cargo build timings. So this option will make cargo generate an extra graph for the build of your crate. So on the slide here, you can see a build graph for 30. And in fact, there are like two build graphs, which I'll get to in a second. But let's focus on the last one first. So on this slide, you can see all of the crates that were built. This is a clean build of 30. So we can see all of the dependencies being built. And there is also a derive feature enabled for 30, which means that we'll have to build 30 derive. So as I've said, as you can see here, the cargo has to build all of the dependencies of 30 before it can build 30 itself. And so we have this pretty long chain of sin, which then unblocks 30 derive, which then unblocks 30. But at the bottom here, you can also see the CPU usage of the build over time, which is something that's also included in the timings graph. And so my CPU is mostly sitting idle for that build, for the most part. And so we're only building one crate at a time, and rustc is mostly single-threaded except for the code generation right now. So we're spending 3 seconds, but we're not really making use of the parallelism here. And in case of 30 in particular, the problem is that since we cannot start building 30 before we're done with 30 derive, we have to wait for 30 derive to finish. That's kind of self-explanatory, I guess. But the 30 traits, they don't really need to wait for either sin or 30 derive to. We don't need these traits to build the core 30 functionality, which is needed by crates like 30 JSON, for example. And so the first tip the first rule of thumb that I'd list is that you should really strive to split up your workspace to avoid these serial dependency chains. So in case of 30, you could extract that pretty much everything about 30 into a separate crate called 30 core, and that crate is what you see on the second graph on the right-hand side. And then you could build that part in parallel with 30 derive. And at the end, you'd have 30 as usual, but that crate would now be way thinner. It would just re-export both 30 core and 30 derive. And that you can already see on the graph here that we reduced the total build time from 3 seconds to 2 seconds, 33% improvement or something like that. Well, you might say that it's not a lot, because it probably isn't. A second, well, who cares about a second, right? But the thing is, especially with such a foundational crate as 30, by pushing things to the left-hand side of your build graph, so by unblocking crates, you might actually cause something like a cascading effect, where unblocking one crate, so in this case 30 core, might allow building 30 JSON in your dependency chain down the line, which then can unblock other crates. And so even though this change by itself might not seem like much, it can actually significantly reduce the time needed to build the workspace as a whole. And even though this is a clean build, as I said, this also applies to incremental builds. So the timing file it doesn't pick favorites, so to speak. You can use it for both the incremental scenarios and the clean ones, and they are just as useful in both cases. And then another thing that's worth talking about is pipelining. So this isn't the build graph of 30. This is a build graph of Z, an excerpt of a build graph. And this is actually the most common one that we run, which involves rebuilding about 40 crates, I believe, at the time. And that takes 7 seconds. So that's still a decent score, I'd say. But the thing is, Cargo will actually, it doesn't have to wait for the full build of your dependencies to finish before it can unblock other dependencies. So at the top here, we have this editor crate, which is what I've modified in this example. And as you can see, there are various dependencies, such as the picker, the second one, which can actually start building before editor itself is done building. And so each node in this graph, so for example, in editor's case, it's quite distinguished that there is this light blue part and then the purple part of the node. And the thing here is that Cargo will start building all of your dependents of a crate as soon as the blue part is done. So just to shed a bit more light on what's going on here, the blue part is the front-end part of the compiler, and then the purple part is the backend, basically. So rustc doesn't need the code gen result to build the dependents of your crate. And so in this case, we can actually start building about, I think, like half a second sooner due to that feature. And once again, if you combine it with the other thing that I just spoke about, which is that you can unblock things for a build way sooner by modifying your dependency graph, that once again adds up. And for these changes to happen, you often don't really have to change much. You might have to move some code around, but other than that, you're not really going to dabble with Rust. It's mostly about inspecting your exports from your crate and seeing whether there is like a disjoint set of export in a crate. In these cases, you can often get away with exporting or with creating a separate crate just for a single type, or well, not a single type. That would maybe be an overkill. But the point is that you should really strive to not have like a god crate in your dependency chain, which we do, by the way, but we're working on it. And so in Z's case, in particular, as you can see here, we're heavily front-end bound, and codegen is not an issue for us. And we could probably try to do something hacky to re-architect our whole app so that there are no direct dependencies between the crates, so that the rebuild wouldn't happen just as often. But we went the other way. And we actually started looking at the profiles for rustc by itself. And so the question that I want to get into now is, how do we deal with build slowness of any single node in the build graph? So we've just looked at your build as a whole and kind of diagnosing it, or like what's wrong with the build as a whole. But sometimes you might want to actually look at the single node in the graph and see what's going on. So for example, you might ask, why does it take 2 seconds to build the editor crate? And so for that, we have to get our hands dirty. And so rustc has roughly, 6 components from my perspective. You have the crate loader, which is just responsible for figuring out where your dependencies are. Then there is a macro expansion. Then there is the intermediate representations, that are created for your code. There are monomorphizations, which we'll get to in a bit and spend a fair share of time on. The cogen and the linking. And cogen and linking, as I've said previously, happen only for the final artifact. And just to expand, because I kind of glazed over it, HIR here refers to high-level intermediate representation, which is one of the intermediate representations that Rust uses, and it's closer to it's pretty close to the way that Rust source code looks like, but it's not well suited for cogen and optimization, and that's what MIR is for. And MIR is where the borrow check-in takes place, for example. And that will come in handy in just a second. So to self-profile Rust, I'm not gonna give you the compile flags for it because there are articles out there. One of which is on Inside Rust blog, which you can look up, and then the other is on blog by Faster Than Lime, which is actually a walkthrough of how he solved his compile time problems by looking at the profiles. Once again, though, each case is different, so we kind of have to look at them ourselves. And in my case, my build graph or the Rusty profile looked totally different than his. And I'm not sure how visible that is. I hope it's pretty visible, but there's one dominating factor in my build, and that's the generate crate metadata. That's basically right before that's the very end of the front end part. And so you can also see here that there is the crate loader, as I've mentioned, the HIR generation, and then at the end, there is this little rundown of the pink lines, which is the cogen part, which happens in parallel. And so you can also inspect the table with the timing with the Rusty profiler. And so let's just look at what's going on with Rusty. And one thing that's worthwhile in particular for me is tweaking the cogen unit. Even though I said that cogen is not an issue for me, we are going to start with cogen because that's gonna come in handy in just a second. So when Rusty cogens your crate, it actually splits it up into n chunks called cogen units. And so these cogen units are then processed in parallel. As we saw just a second ago, there were like many LLVM threads that were all cogening, and that cogen part didn't really take that long. And so one thing that I found useful, and it's not really a tip or anything, it's just to kind of show that there are different factors that influence your build, is that you can tweak the amount of cogen units. As by default, it's 16 for release builds, and then 256 for dev builds. And the trade-off here, if you have more cogen units, is the worse cogen quality, which is fine-ish in dev builds. So some people even run with just one cogen unit when they want to achieve like the best cogen for a given crate. And for that specifically, we found that having that many cogen units was overkill, and it really didn't contribute. Well, it didn't contribute much to our incremental build time. But just to give you a sense of what the impact of this change was, when we dialed back our cogen unit to 16 for that build from 256, we went from 29 seconds for an incremental build of like a deep dependency chain to 22 seconds, and then 13 seconds for like a shallower build to 11 seconds, which isn't too shabby for changing a single flag in your cargo.toml file. Obviously, it might be different in your case, but once again, the point here is that you can tweak your build in a way that will make things a bit faster. And then another thing that we probably need to touch on, or definitely do, is generic functions in Rust, because that's another source of problems in Rust when it comes to incremental builds. So generics are cool and all, but they have to be codegent for each crate in your build graph. So on the side here, we have three functions that use generics, but only two of them are actually going to be generic functions that are codegent in the downstream crates, in the dependence of this crate. Let's say that this crate is called A. And so the first one is obviously generic. When we look at the HIR of crate A, it's also generic because as you can see, there is this crate mount on impl copy. I know it's not valid Rust, but it's just an HIR. And then the third one, which, just to go back for a bit, returned an impl copy, is not generic because that's there is a type inference at play, and so we only constrain what the caller of this function can do, but the function itself will not be codegent in the downstream crate, which we can see at the MIR level. So at the impl ret, we now have the concrete return type of that function. So now let's add crate B into the picture. So which of A's constructs will be monomorphized in B? The short answer is the generic function. Whenever you have a generic function in your code, and there are other crates that use that function, you'll pay that cost of the codegen multiple times over the build graph. And there are tricks to make it less severe. The one that's often thrown around is that you can have so-called inner functions. So, for example, let's say that you have a function which takes something that implements as a ref, which is pretty common, in fact. So there is this function body, and assuming that all of the function body is within the same generic function as monomorphizes everything function, the function body, which uses this reference to a string, will be codegent in all of the crates that use that function. So instead, you can create a non-generic function. It doesn't really have to be inside of the body of monomorphizes less. It's just, well, a convention that I use. And in this case, the monomorphization will still take place, obviously, because you have this, well, it's a generic function after all. But now, instead of carrying along the full body of the generic part or the non-generic part, we'll just call into this parent crate, so to speak, and that's it. The other thing that you can do is you can just use the dim dispatch to just kind of avoid monomorphizing in the first place. So in case you're using a function that takes a dim object, you'll actually just have one function in the parent crate, assuming that there are no that the function is not generic otherwise, so it has no other generic argument that I spoke about previously. Then you might actually still find yourself still waiting for the generics, and in these cases you might want to reach to LLVM lines, which is just a helper to. This tool will just show you what how much LLVM IR is in a given crate, and how many copies of a given function there are. So in this example, I mean the slide here is cropped, but going from the top, I can see that I have about 1.8 million LLVM IR lines, of which 70K, which is the first entry is the biggest contributor, that's GPUI update, and that contributes to about 3% of my LLVM IR. But we're talking about generics here, so that's not the point. The point here is that the LLVM IR stems directly from the generics that you have in your crate. So that means, looking at the copies column, I have about 1,000 copies of that function, this function is obviously generic. So that means that I have about 1,000 instantiations of this function across this single crate. So if I were to go hunting for places where I'm instantiating unreasonable amount of code, I would reach to LLVM lines, even though in case of dev builds in particular, rustc has your back, so to speak, because there's this optimization at the rustc level, which applies to all users of Rust, really, where if there is an instantiation of a given generic in the function or in the crate that you depend on, that a crate A depends on, there will be no instantiation in that crate. We'll just grab the existing instantiation from elsewhere. And that really helps. There are small caveats to that, as in, for example, if there is an instantiation in your build graph, but it's not an immediate dependency of a crate that you're currently compiling, then that's not going to be reused. But in practice, that's not really that big of a deal, I'd say. And if you're looking to optimize your release build times and you're willing to use nightly, that's an option as well. This, as I said, this is running even if you're like using stable Rust. It's just not exposed to you as a knob for you to configure. So if you're running a dev build, you're already using it, you cannot disable it if you're using stable, and you cannot enable it for release builds if you're using stable. That's the only limitation. And just to add one more thing, when we were like experimenting with this, with using shared generics for a release build of that, the compile times went down by about 30% for us, which was not too shabby of a result. There could be cases, though, where you've tried everything, you went through the profiles, you spend however much time you need to figure stuff out, and nothing works. You've tried the train lift as the alternative codegen backend to make the codegen faster. You might have tried tools like sccache to just cache your build so that you don't have to wait. Maybe even a faster linker. And sadly, there are cases where you'll run into a wall. And the fix is simple. Obviously, you can contribute fixes upstream. And I really, really mean it. As there is a limit to what you can do with a compiler, obviously, in some cases, your code will be just slow to compile, and the solution is to just maybe rewrite the code. But there are cases that are pretty apparent when you look at the profiles that are just compiler problems. And so the thing is, the developers of the compiler cannot know that. As in, your project is not in their test corp, and that's that's the problem that we've had with that as well. Just because when we've reached out to or started like talking about our compile times in public, we've heard that that our project doesn't really match the like the task corpus and what the compiler developers usually see when they profile their build. And so it really makes sense to just get your hands dirty again, because nobody is going to fix it for us. And at the same time, there are things, or there are like changes or improvements in the flight that are likely to improve your builds. For example, there is an ongoing effort to parallelize the front-end part of the compiler, because I should have mentioned it, or maybe I did, but the code gen part is the only parallel part of rustc right now. But that won't necessarily help you if you don't have any cores to use with that parallel frontend, right? Another thing that's going on is that there's an ongoing development for a new linker called Wild by David Latimore. And sure, this is going to help me. This is going to help that. But maybe for you, the linking is not a problem at all. So while these are good things to work on, I don't think we should rest assured that things are going to be fixed for us. And so, once again, it's on you to raise the issue. And honestly, we did. And ever since we've gotten involved with rustc development, our incremental build times were reduced just with compiler changes by about 20%. and that's now in the latest Rust release of Rust 1.85. This includes 3 PRs we've contributed upstream, and one change to MIR processing that one of the Rusty developers landed after looking at the build profiles for us. And we also have another PR in flight, which eliminates some of the slowdowns still, plus the MCP for the compiler, which stands for the major change proposal. So we actually want to start, or what we struggle with in particular is that if you recall the build graph for that, whenever we change the crate that's deep in the build graph, we always have to rebuild every crate after that, because as I said, the dependence of the crate that you're rebuilding always have to be rebuilt. So that's a problem for us, because that adds unnecessary overhead, as there are cases where you can actually skip the rebuild. For example, when the public API of the functions doesn't change. Right now, it's sufficient to touch the source file in one of the crates, and that will trigger a rebuild. So yeah, that's a big problem for us. But once again, that's something that we're looking to fix. And you might also have your problems, but you're also capable of fixing them. And I swear to the organizers or whoever that I've landed 2 very simple changes. I swear, I could show you the diff offline, and these are the changes that anybody could make if they spend the time looking at the profile of their build. And so the point here isn't that we should start, mailing the build profiles to Rust developers. We shouldn't be nagging them. That's not the point. It's just that if compile times are a problem for you, there's a very high likelihood that you have the agency to fix them. And it's not something that you have to live with. And that's just my point. So yeah, it's not out of your reach, and all you have to do is just start profiling. Oh, sorry. Yeah, I killed it. Yeah, but that's the end. So just go out and profile your builds.
Okay, we have some questions. So the first one is, have you used the mode linker before? If yes, have you encountered any benefits or drawbacks?
I'm mostly using macOS right now, and for a brief period, I did use a mode linker or a version of it for Mac, which was called Sold, funnily enough. But long story short, I didn't use it for long, just because Apple released an update which fixed like 2 years ago, I think, which significantly improved the performance of a linker. But I don't want to. I do not want to spread rumors, but I think it's worth checking out. Yes, especially if you're like on Linux.
Okay. What is business domain in Z in where you need to have time contract with compile time with max a few seconds? Maybe this is internal engineering challenge.
So I'm not sure if I understood the question well, but it's just there are no constraints, and it's just the pain that we feel every day, so to speak. Not sure once again if that answers the question. So if there's, it depends.
Okay, is there an author of that question here in the room? Okay.
My question was about the business domain. So, for example, if you do the trading, for example, this is a domain for finance, you probably need to have a faster time to build piece of software, because you rely on, let's say, milliseconds. Yeah.
So the business domain here, I guess, like the compile times are not a product that we offer to our customers. We are in IDE business, and so it's just that we don't like waiting for builds when we're developing the software that we then offer to clients. So there is no money in it, if that's what you're asking.
The next question is from Arto. Are you able to use the cached generics thing in production builds in nightly?
Yes, and as I said, the shared generics have been enabled by default for all of us for, I think, for 5 years at this point. so they're unstable. You can use them in release. With the only caveat is that if you're using the shared generics, you might get worse code gen, just because rustc won't have the visibility into the into the body of the generic that it's instantiating. So there is going to be a drawback in that, but I think it's still worth trying out and measuring whether there is like a performance penalty for you. I don't think there would be, but once again, just do your own measurements. But yes, you can use it in nightly just fine.
Have you used SC cache before? If yes, in what way? And have you noticed any benefits?
No, I mean, I tried to use it, but I found that for our use cases, we've had like very low hit rates on it, just because like each invocation of rustc in these cases, like changing async rate will be slightly different. So it doesn't apply to my use case. That's just what I'm saying.
The last question, do you have a chance to do profiling production con? I mean, something what works too long and what challenge it was?
Once again, is it about compile times or just profiling in general?
Profiling in general from production. So you detect something and you would like to go to the profiling mode. And what kind of challenge do you have from production?
So yes, I do that a fair bit. So in particular, with that, I did things like profiling the performance of font parsing off the top of my head. And so the challenges here were mostly, I'd say the biggest challenge is not really around the profiling part. It's about getting a consistent reproduction case and understanding what the problem is for the customer. As in our case, once again, we're building an IDE, so you might run into into a client who sees weird behavior, bad performance, just because of their operating environment that you obviously don't always have means to reproduce. Then there's also the settings that these are quite easy, so to speak. And then there are also some cases. I recall that we've had like one performance problem where somebody was scrolling in an unusual way. So try to reproduce that, obviously. So these are the biggest challenges. If you can iterate on the slow part, that's usually not the biggest problem, at least in my experience.
Okay, that was the last question. So thank you very much for your talk.